architecture, and this can show you on a function-by-function basis how you're doing. And so for a lot of these routines, that's not important, but here's the one that we were most interested in because it was taking the most time, as we saw here, right? In our main production, it was this elect function that was taking the most time. And so, so here you can see that one is up there. It's in for an x86, which I think has a peak of 2 floating point operations. I think this is probably an AMD Opteron. So this is getting about 30% of the peak performance in that main routine. Yeah, there it says right at the top, peak is 2. Okay, so this is just an overview again of this process, and we can show in more detail exactly how to get to those different things here in a minute. So now we've measured the performance, and we want to look at regions of the code that are inefficient. So that's where we're at right here. We're looking for inefficiencies. This one, looked pretty decent, but it turned out that in this case, we can do much better in that routine if we make sure that we get all of our functions inlined. There's a number of small functions called, and so just with the compiler flag there, that there was a compiler message saying it couldn't inline some functions, and so we gave it an option that forced it to, that they gave it the information it needed to do that, and so now we can check and see how that affects the performance. We see that the code speeds up as a result, and we can see that it's due to much better efficiency in this main elec routine. As I mentioned in the beginning, we're focusing on the tools here and how to use them to find issues. Solving any particular issue is going to be specific to your application. There's lots of resources out there to look at this. I found a book. There's not a lot of books. There's information on the web, but there is one book. It's getting a little bit older, but most of the information there is still pretty pertinent. The thing that's kind of missing there is the whole multi-core thing. But the basic performance optimization techniques things are in there. So I just put that there for reference. And also, there's a number of, NCSA has a number of CI tutor courses on optimization. And there's one called Performance Tuning for Clusters. And that one also has a good introduction to the basic things you look at. If you found a region of your code that was important, that was getting very low floating point operations per second, you could check also, you could run with PAPI counters to look at cache misses and see if that's the problem. And most of the time it's something like that, where you're just having bad memory access patterns. And so then you could isolate that, and isolate exactly where that's having a problem, and how bad it is, and so then you can take a look at the code and look at try to drill down and see what performance, if any of these performance tuning techniques would be suitable for addressing that in your code. Okay, so let's talk now again about we've got the functions that are important as we scale up, and we see where it's spending time. So now we want to see where the issues are, if there's load balance problems or serial regions where previously time was not very much time was spent when it was running in serial, but now we scale up, and it turns out that these serial regions become bottlenecks. So this is sort of for reference. These are instructions on how to do this when you open up a profile with Paraprof. So if you have a phase defined, like I showed before, then you can right-click on the phase name and you tell it to show the profile for just that phase, and that will isolate just that phase that you're interested in. You can look at then the load imbalance in particular functions by just clicking on the function name, and it will show timings across all the processors. And then there's a couple other options that make it nice to look at. It by default tau normalizes the timings when it shows them, so you can't see which processor is taking more time. It's just a nice rectangle. I'll show that. So if you take that off, it's easier to see. It's easy to see where the load imbalance is. You can also separate out the function calls. So here's just an example of if you isolate. So if you left click on the function name, then it will show you the timing on across all the cores or all the tasks, and so then you can see where if there's a particular function that is having a problem that's causing a bottleneck due to load imbalance, like this one here. Okay, so this again is mostly for reference. I think we'll go through this in actuality so you can see how it's done. But one way to sort of isolate serial bottlenecks is to do just a scaling study, and then you can look at the different you can look at the execution time function by function as you scale up. So these, again, I'm going to kind of skip over this because I'll show you how to do that. But you can look back at that for reference. So here's what I'm talking about. So this is the mean execution time. So in the blue, we ran on 4 processors, and that was a run over 4 processors. And in the red, that was a run over 16 processors. And so each of these pairs is a particular function in the code. So you can see how as we scale up, how the time decreases, and you can see how well it's scaling on a function by function basis. So now we may have already looked at the overall parallel scaling, but now we can look at it on a function by function basis and see which of these functions is becoming a serial bottleneck in our code, which ones are scaling well. So we're going up by a factor of 4 here, from 4 processors to 16. So the time should decrease by a factor of 4. So if we see 25% next to it, then we know we're getting perfect scaling. So this one's doing pretty good. This one's about perfect. That one's about perfect. But then we start to run into some of these that are not scaling at all or not scaling as well. And you can see that these are some of the routines that didn't take up very much time on 4 cores, but now as your total time starts to decrease, I believe this is the total time right here. I've cut off the labels here. So I think this is the total time in the phase. And so this was the overall scaling for the entire MD loop. So now we've only got 14 seconds in that loop. And so now some of these, especially as you go over 16, you go up to 32, some of these routines that aren't scaling are going to become a bottleneck. So you can find which ones you need to focus on and address. Maybe it wasn't important to parallelize them before, but now it'll be important if you want to scale up. So this was what we found in this unres code. And I think the reason I cut that off is because this is, I think, part of the exercise that some of you have is to identify the obstacles to scaling and that we found in this unres code in this sort of real life example. So what we did find is that there was one of these routines that they didn't think was important in the code, and as they started to scale up, it became a major serial bottleneck, and so they just had to parallelize it, and it wasn't that hard to do. They just never thought it. They just didn't think it was that important. It was like it wasn't an n squared operation or anything. It was, but it still had to be parallelized. So, and then there was some significant load imbalance in these among some of the other routines. So there was a serial bottleneck, and then there was some serious load imbalance that we found. This is actually from the. That's actually fairly minor because the time on that one, it wasn't as significant. But you'll see it in the exercise if you go through it. But we were able to point that out to the group, and they went back, and this is one of those cases where the solution was that they thought that the algorithm that they had been using would be load balanced, and by doing the profiling, they saw that in fact it wasn't. And so they re-examined the algorithm they were using, and it turned out with a little more effort, they were able to find a better algorithm that not only was it better load balance, but it actually required fewer operations. And so this was a big win. And so because they were able to find a better algorithm, they not only increased they not only got it load balanced, which helped the parallel scaling, but they also got it to run faster in serial, like 4 times faster. So it was a big, for not a whole lot of effort, it was a major win for their code. Now, because they made it faster in serial, they also made it harder to scale efficiently, because the more efficient your code is, the harder it is to scale. That's a good thing, because you don't want to scale an inefficient code. So now that changes, that shifts again where these bottlenecks are, and so you have to go back and reanalyze. And so this was actually the snapshot afterwards where we're looking at where is there still some load imbalance. So you can see in this view, so this was what I was talking about in that main view. If you go up into the options and say don't normalize anything, and then you can also tell it to separate these functions out. Each one of these is a different function, and so then you can easily see, where the load imbalance is, and if there's any, where do you need to go next to start to look at addressing problems. So that would be here. So you can see that it looks like that all these other cores are spending a lot of time in MPI barrier because this one's taking a long time to finish this in this particular function. So that's something to look at and see if there's just something algorithmically or implementation-wise that you can do to eliminate that bottleneck. Okay, so when you're trying to identify the cause and effect of some of these bottlenecks as far as communication goes, then sometimes you might want to get a time-resolved look at how this thing actually unfolds. Who sends messages to whom, and who's actually in real time what's happening. So for that you can use tracing, but you have to be really careful with tracing because it generates a ton of data. So you need to get some very specific information. So everything we did previously, leading up to this point, identifying those key functions, finding out which functions are important, especially as you scale up. Now this prepares us to take a step like really digging in deep and looking at a trace of the application. Because you'll only want to trace those key functions that you identified to limit the amount of time that you're spending in the amount of data that you're generating with this trace. So now we get back to the point that I brought up earlier about using this call path information. So if we're trying to isolate the MPI calls and look at these MPI calls that are important, if we don't get the call path information, then all the information about every different type of MPI call will just all be lumped together in one thing, and you won't be able to tell where in your code it's originating. But if you run it with the call path, then you can actually see from top to bottom where that call is. So we look down this list, and we're doing okay, but then here we see this MPI barrier issue that we saw before. But okay, so here's the thing to take note of with when you have call path turned on. You see that are two these two MPI barriers sitting next to each other. The first one, if you have call path on, so this is only if you have call path on. If you have call path on, then it will show you first. It will show you just that function all lumped into one, just like you would see if you didn't have the call path on. Okay, so this is all. So this right here is all you would get if you didn't have call path on. This is the total time spent in MPI barrier. Everything that called MPI barrier during the course of your run all gets lumped into this. Okay, So then that will be the max